Hello. Welcome everybody to the GW at 10, Gravitational Waves at 10 years, celebrating the direct discovery of gravitational waves by LIGO in 2015. I was just telling Scott here the story about, I was a grad student at UChicago, and the way we figured out that something had happened at LIGO was Daniel Holtz, who was a LIGO collaboration member, just disappeared from group meetings for months now. We've never seen him. We realized, okay, either something bad has happened or we found gravitational waves. And it's just an amazing feat of collaboration over decades between scientists, engineers, and all that, that from, what, 91? Right? Early 90s, LIGO?
So LIGO, I mean, it predates that, really. Yeah. So attempts to get it funded started in the 80s.
Yeah. So
and Ray Weiss did the end-to-end modeling of what it would take in 1972.
Wow, okay, so that long. So that's long-term project building, just to find gravitational waves. So now we're celebrating the 10 years of the discovery. And for the first talk, it's great to have Scott Hughes here. Scott Hughes did his PhD with Kip Thorne, and then stints as a postdoc at University of Illinois, Urbana-Champaign, and University of California in Santa Barbara. And now he's a faculty at MIT. And it's a pleasure to have him here give the first talk in this series about high-precision gravitational waveforms.
All right,
Scott.
Thank you. It's wonderful to be here. I gave a talk last week to the students at PS University, literally 12 hours after I landed in the airport. And so it's nice to have actually gotten a couple nights of sleep and be able to do this feeling a little bit more alive and conscious in front of you now. So indeed, I want to tell you a little bit about this. It's been an amazing 10 years. And I want to talk about my personal view of what I think, from a theoretical perspective at least, where the future of this field lies and where I think some of the most important work and the excitement comes from. I want to begin, though. I like sometimes, before looking forward, to look back. And I like to begin. I have a couple parables I want to tell in this talk. So this is a parable that means a lot to me personally, because I was connected to this. So when LIGO was originally under construction, that is indeed what started in 1992. It's when construction was authorized and it began. If you go back and you read a lot of the literature about what sources we expect to measure, it all focused on binary neutron stars. And the reason for this was that we knew binary neutron stars existed. We could see them as binary pulsar systems. We were confident that we knew how to model the gravitational waves that they produced. And so, and because we observed them, we could see how many there were in our galaxy. We had an idea where they came from. We had some confidence in the event rate. And so when you talked with, to be perfectly blunt, when you talked with funding agencies, you always tied things to the event, the sources that you were confident existed. Now, so that was why binary neutron stars were all over the literature. However, it was understood pretty well that if you look at the sensitivity of these detectors, that they were really perfectly placed to pick up the binary black hole signal, assuming we could actually model it properly. So this is a plot from a figure that is actually part of my PhD thesis. So the dashed lines here give some estimates for what the signal strength would be in spiral merger and ring down for a couple of binary black holes merging, and comparing it to some crude estimates of what the noise curves might look like there. One of the things that we saw when we did this was that the piece of the waveform that the detectors were most sensitive to were the ones that theorists did not know how to calculate. So the purpose of one of the main purposes of writing these papers was essentially to yell at the community that was developing numerical techniques for modeling these things, saying, this is going to be important for astrophysical sources. You need to figure out how we're going to calculate these. Now, we put all this stuff together. So this is a paper I wrote with my colleague Anna Flanagan. We actually have this very wishy-washy statement that binary black holes might well be the first sources detected by LIGO Virgo, which was kind of even that wishy-washy was a bit of a bold thing to say. Okay, everyone was saying, no, binary neutron stars. We don't know anything about these binary black holes. And indeed, a lot of their astronomer colleagues at that time were telling us that black hole binaries are not to be expected at all. Okay, if you go and you look at why Flanagan and I were arguing that binary black holes might be the first source, it was essentially because we found that they were very strong and hence measurable to much greater distances. the volume of the universe might be a factor of 1,000 or 10,000 more than it would be for binary neutron stars. And so he said, look, even if the rate is small, multiply that by 10,000, you're going to get a big number. And people like Lev Jungelson were saying, okay, fine, but 10,000 times 0 is still 0. And that was essentially what papers like this were telling us. This particular paper, by the way, comes from a conference presentation. In my 5th year of graduate school, my colleague Anna Flanagan and I gave some talks at this meeting in Paris where we described the importance of binary black holes. And it was immediately followed by this talk saying, take that previous talk and multiply by 0. So as a 5th year graduate student, it was a little, I was on the job market and I kind of went, oh, what have I done with my life? Fortunately, I had Kip Thorne as a PhD supervisor. And so he wrote on a draft of our paper specifically about our prediction. I think you will regret not phrasing this prediction more strongly when LIGO is regularly measuring merging black holes in about 5 years. Notice he wrote that in 1996. 5 years from 1996 was 2001. So Kip, I think, got the science exactly right. He is a very optimistic person, though. And so I think he was a little optimistic on the time scale by about 15 years, which is actually, if you look at some of the bets that Kip has lost, only being off by 15 years isn't so bad. So all the wisdom from our astronomer colleagues was gradually evolving over the years. And indeed, by the time we approached the mid-2010s, a lot of astronomers were agreeing that the mechanisms that produced no binary black holes were probably flawed. And indeed, this changed in an instant on September 14th, 2015. So from the standpoint of a relativity theorist like myself, one of the things that I want to emphasize is that the waveforms that were measured, so these are just the very first event that was measured, and this follows for every event that's been measured since then, you need consistency with general relativity for the global space-time dynamics in order to explain these data. This was really the first sort of strong field dynamical test that could be applied to general relativity. There were a lot of really interesting strong field tests that can be done by observing things like accreting neutron stars, accreting black holes, but they didn't really have dynamics in them. This was a case where the space-time was rapidly varying with time. And that really changes things. And what I think is an important point is that we have now measured over 200 events. So in this plot, all the blue events are our knowledge of black holes from gravitational waves. The red things are all the black holes that are observed using X-ray telescopes, optical telescopes, sort of traditional astronomical measurements. And it's just been kind of amazing that these events just keep happening. And we seem to have a universe that produces lots of black holes, masses similar to that of massive stars, and they find each other and they merge. Recently, the band by which we can measure these things has gotten wider. So long-term monitoring of radio pulsars was long expected to be sensitive to what you kind of think of as a hum of sort of the superposition of many, many sources from much more massive black holes filling the universe. And we rerun that little animation. The sketch of the idea is that in the absence of a gravitational wave, the pulses from a particular pulsar will basically constitute a beautiful clock, some of the comparable to the best atomic clocks we have here on Earth. When a gravitational wave comes along, it's going to disturb that. And as long as the signal, as long as the disturbance sort of wiggles that signal more than your intrinsic noise, that is a way that you can try to measure the gravitational wave. Now, doing that with just one pulsar, you would never believe it. So what you want to do is look for it over many widely distributed pulsars and look for the correlation pattern that you would expect for a sort of a stochastic superposition of many quadrupole waves. And that is, in fact, something that was just announced a few years ago by an international collaboration. I believe India's Giant Meter Wave Radio Telescope is participating in this, one piece of it. I'm focusing on the presentation from the North American nanograv analysis, in part because one of my graduate students led this analysis, and I'm very proud of her. But what they were able to show over 15 years was that the quadrupole distribution emerges from the data. And when you, whoops, I don't have that slide. When you look at the behavior of what the power looks like over time, the best explanation for this is a population of millions and billions solar mass black hole binaries that are producing gravitational waves and filling the universe with their signal. By the way, the periods associated with these waves are months and years. So this takes a very long time. That's one reason why it takes 15 years for the signal to build up and to stand up in the data set. So what's next? These past 10 years have been amazing. Okay? Seeing the very first discovery event, I rank as one of the most emotional things in my life that I have actually seen. Certainly in my career, but even in other events in my life. It was one of the most powerful things. I'm not going to talk about the binary neutron star in this talk, but that was also something that was something I'd long anticipated, and it was just beautiful to see. And I won't deny that once we sort of had those discoveries, I kind of went, well, now what do I do? All the beautiful discovery, the sort of finding the gold bars, that happened. It's like, okay, now what do we do with them? This field is evolving into a data-driven field, just like every other field in astronomy. We are at the point now where we're regularly detecting these things, we're measuring them, we're using them. One thing that is really, I think, driving what we do is that the detectors are getting better. Theory needs to get better to keep up with them. Okay? In particular, as time goes on, so here's a map of all the different instruments that are not all of them are actually being built, but this gives you an idea of sort of the landscape of current and future instruments, the space-based instrument that is on the table. As we develop these things further, the noise floor gets pushed down. We have more sensitivity. Each event, we are accumulating more signal-noise ratio per cycle, learning more about the nature of the signal. We are opening up different bands. In particular, when the laser interferometer space antenna LISA flies, that'll be sensitive to gravitational waves at much lower frequency, which opens up a completely different part of the gravitational wave spectrum. It'll be sensitive to things from massive black holes, not just the stellar mass ones that we are observing today. And when we have wider bandwidth, signals will be in band for longer and give us more details on the wave's evolution. So a signal that comes in here on, say, the Cosmic Explorer low frequency line, it might be in band for tens of minutes before it coalesces, as opposed to of order minutes or seconds in the current LIGO detectors. So this will give us much more precision on the gravitational wave properties. So what have we learned so far from these things? Well, one of them, I would say the number one bullet point is general relativity works. Many of us came into this field thinking, I'm going to test general relativity. And I continue to think this is something we should keep working on, but let's be blunt. Einstein was pretty smart. And it turns out, if you just take the vanilla Einstein theory and you apply it, you can describe the data really, really well. Okay? Maybe there'll be a crack at some point, but I've told several groups today that if I were to take the money that's currently in my wallet and place a bet, Einstein right, Einstein wrong, I'm going to bet on Einstein right, at least for the duration of my career. We've learned that the sources that produce these things come from a wide range of masses and mass ratios. So we've seen black holes down to about 6 solar masses, up to about 200 solar masses. We've seen several neutron stars, and we've seen systems with mass ratios that range from nearly 1 to 1 up to about 10 to 1. In fact, that might go a little bit beyond this now. I should probably update this slide. We see clear evidence that in many cases the black holes are spinning. Broad posteriors means that we're not able to pin down those spins very precisely, but we have clear evidence that it's at least non-zero. Black holes in general relativity are only characterized by mass and spin. So we're zooming in, and we're starting to pin down the parameters that describe these things within general relativity as well as we can. We typically do not yet have much great information about the spin orientations. I'll come back to that a little bit later. So this information is good enough that we're starting to learn about possible progenitors. It's turning into an astronomy machine. We're using this to learn about the populations that produce these binaries and feed to these events. But there's a lot that we expect that we have not seen yet. So I'm going to focus on binary black holes here. One thing is that we have not yet seen any event that clearly has orbital eccentricity. Now, there may be orbital eccentricity in some of these, but all the data are consistent with E equals 0. Okay? Perhaps when we have more cycles and there's more time for the effects of eccentricity to build up, we'll begin to see everything, but it's not there yet. We have not yet clearly seen evidence that the spins are strongly misaligned with the orbit geometry. And this is interesting because it tells us, if this holds up, it tells us something about the formation mechanism. If you have two black holes that form from two stars, you expect those stars, through tidal interactions, to align their spins with each other and with the orbit. They'll then go through supernovas that may sort of jostle them around a little bit, but they'll still be pretty close to each other in orientation. On the other hand, if they form in, say, a dense star cluster, you kind of expect the spin-orbit alignments to be random. So we haven't seen strong evidence for that kind of misalignment yet. But notice I said strong evidence. There is one event that is actually quite well fit by a misaligned merger. This event, very strong. It's a very high mass system. There are about 3 or 4 cycles of gravitational waves in this thing. And so when you fit this, the way that we think it looks like it's probably misaligned merger, it has to do with the spectrum of waves that produces it. It's best fit by one that requires strong misalignment. But to be perfectly blunt, any signal that you're fitting that just wiggles 3 or 4 times, you can fit a lot of models to that. And so this is evidence. It's decent evidence. I want better evidence. We have not yet seen a fascinating effect that I'm going to tell you a little bit more about in about half an hour, called tidal heating, which in the context of most astrophysical systems is sort of the heating of a fluid in a body due to gravitational coupling between the members of a binary system. There's an analogous effect that happens in binary black holes, which ties to the beautiful equation of Raychaudhuri, as well as to the theorems of Hawking and Hartle. And indeed, black holes don't exist in a vacuum. They should be interacting with their environment in some sense. We haven't seen any strong evidence for this yet. In fact, I'd say we really have no evidence for this. But we expect this to be an important contributor with some of the future measurements that people are thinking about. These are all effects that we are going to need to know how to model properly so that we don't confuse them with each other. We don't confuse them with other effects. In particular, if what you would like to do is say, I'm testing the nature of gravity, you better make sure you have all these other things right, okay? I mean, anyone who follows particle physics, it's not that, it happens from time to time. Someone sees an event at 2.1 sigma, and you're like, oh my God, we finally have evidence for something beyond the standard model. And then you get better data, like, okay. I would like to avoid the systematics causing us to make that same kind of a thing. I'm sure we will, but I do my best to prevent that from happening. I have another little parable that I want to tell you about that helps to illustrate how subtle some of these effects are. So the 15-year nanograv data set shows strong evidence for the quadrupole distribution. Interestingly, when the 11-year data set was first analyzed, there was a residual in it whose amplitude was at the level that was expected for a gravitational wave background. So the initial fit are these dashed lines. Okay, and so the different things here are different analysis chains. And what they showed was that the most likely explanation for those lines was some kind of a signal at an amplitude in these units of about 10 to the minus 15, which is right about where people expected the stochastic density of gravitational waves to be. So they went, oh my God, they were not expecting it to happen this soon. They said, perhaps these waves are even stronger than we realized. But when they looked at the distribution of correlations, I mean, it's pretty noisy. It turns out if you do a fit to this, there's a small but significant dipolar trend. Now, when you have the wrong gravitational dipole, that means you have the wrong center of gravity. You have the wrong center of mass. And so what they realized was going on here, so bear in mind, these things are taken by radio telescopes, which naturally are on Earth. And so they are not in an inertial reference frame. You have to correct for the fact that the Earth is going around the sun, the moon is going around the Earth, the sun and Jupiter are going around their mutual center of mass. You have to correct for all of the effects that set the barycenter of the solar system. And so what they did first was they said, well, let's let this, let's treat the, let's use this data set to try to estimate where the correct barycenter would be. And what they found was that if they, and this has actually been revised by later better measurements of the orbit of Jupiter, they found that they indeed had the wrong barycenter when they did their initial measurement. And when they put in a correction, the strong evidence went away. Now that correction that they needed to introduce moves the solar system's barycenter by about 100 meters. So what this is essentially saying is that the gravitational center of mass, and it's mostly the sun and Jupiter, was off by about 100 meters. That nearly led to an incorrect claim of a detection of gravitational waves. Actually, they wouldn't have done that because they knew that the residuals didn't have the right distribution. But people got really excited about this briefly. And I think the thing which I want to emphasize with this is that it really demonstrates how subtle effects can come in and really fool you. So how do we do modeling without systematics? when you're a gravity theorist and you're trying to model a binary black hole system, one of your major challenges is we think of it as a two-body system, but it's not. It's a one space-time system. It is one space-time that starts out as two well-defined black holes in the distant past, and it's a single black hole in the future. But what you need to do is essentially take the Einstein field equations, take the data that describes the thing which is described as two black holes in the past, and evolve it forward. So you really need to figure out how to do that and then extract from the data the characteristics of the binary and its members in a way that hopefully doesn't introduce any systematic effects. That's challenging. And so I am intrinsically a fairly lazy person. And so what I wanted to do instead is find an easier problem to look at. And a particularly clean limit of this problem is what you get when one member of the binary is much smaller than the other. The reason why this works out really well is that you can think of your binary as being dominated by the properties of the larger object. Okay, we can just take that as the exact Kerr metric of general relativity, and then I can perturb it by the properties of the secondary. And this will turn the complicated nonlinear mess of the Einstein field equations into something that is much more tractable. It sets up a set of perturbative equations that I can solve with much greater precision and accuracy. It also happens to correspond to a target for the space-based gravitational wave detector, LISA. So this sort of idealization, which partly motivated just because it's a much cleaner problem, exactly describes what you get when you have a stellar mass black hole scattered onto a strong field orbit of a massive black hole in the core of a galaxy. Now, it's actually expected that events like this are rare per galaxy, but they generate pretty strong gravitational waves, and expected that LISA will be able to detect them out to a redshift of order 5, or maybe even, depending on the mass of that secondary, 10 or 15. Interestingly, we may already be seeing things that are very similar in certain X-ray sources. I'm going to talk about this a little bit towards the end of my talk, but there's at least some evidence that events like this are occurring, and they're related to some of the stellar disruption events that people are measuring when ordinary stars are disrupted by being scattered onto very similar orbits of their black holes. All right, so I'm going to get a little bit technical for a few moments. Let me tell you a little bit about how we model these strong field binaries. So to take advantage of the fact that my system has a small mass ratio, what I'm going to do is treat the space-time of my binary as the exact Kerr metric of general relativity and a perturbative series that is organized. I'm going to use the mass ratio of the system as my control parameter for the perturbation theory. So I'll have a correction at first order, a correction at second order, go as far as your stamina allows. I'm actually going to focus mostly on first order stuff because it's, at the moment, that is the bit that we understand actually very, very well. Okay, second order, we're starting to get some really interesting results in some special cases. There'll be a lot of effort on that. So when you do your GW20 meeting, maybe people will talk about that then. Once you have your space-time under control, you describe the motion of the smaller body in this space-time. And so those of you who've taken a general relativity class know that when the right-hand side of this equation is 0, that gives you the geodesic equation that describes the motion of a freely falling body in general relativity. So what we're going to do is correct the geodesic equation by adding some forcing terms that arise from that small body interacting with its own space-time perturbation. And then finally, once that is done, we can integrate up the motion and we construct waveforms. Okay, so I'm going to tell you about the way that we make the waveforms and some of the things we've learned along the way. So first of all, one thing we find is that we need to have a really good way of studying the equations of motion of that body as it moves around my black hole. This, fortunately, can be done very, very simply. Everything is described in the classic textbooks. It is true that we need to organize it a little bit better in order to do things very precisely. So to give an example, if I go into my favorite general relativity textbook and I look at the equation of motion of a body around a black hole, what I'm going to actually do, let's just focus on the radial motion. I'm going to reparameterize the radial motion of a body that's in orbit around a black hole using a form which, if you study Keplerian orbits and Newtonian gravity, this is a form that will look very similar. Okay, so this P that's in the numerator is called the semilattice rectum of the orbit. It's simply related to the semi-major axis of an eccentric orbit. E is the eccentricity. Chi is an anomaly angle. And then I develop an equation of motion that relates that anomaly angle to the evolution of that anomaly angle to the anomaly itself, to an anomaly describing the angular motion, and then conserved quantities, an energy, an angular momentum, and this thing we call the Carter constant, which is essentially the rest of the angular momentum in a certain limit. A little bit different for a rotating black hole. So, okay, great. That gives me a way to describe motion. Let's look at what that motion tells me. So this is something that we totally understand. And what's kind of cool is that it has a prediction for the motion of bodies moving around a black hole that is quite familiar. So with some special twists added. So what you see when I look at a body orbiting a black hole is that it's completely described by 3 frequencies. So there is an omega phi, which tells me about the time scale it takes for a body to go around the symmetry plane of the black hole. There's an omega theta, which tells me about its motion sort of up and down above the equatorial plane of that black hole. And there is an omega r that characterizes how long it takes to go back and forth in its eccentric orbit. All 3 of these frequencies are identical to one another at very wide separations. But as I move into the strong field, they become quite different from one another. You can kind of think of this, I like to think of this as sort of like a Zeeman splitting of the Kepler line. Okay, space-time curvature is playing the role of a magnetic field here, and it's taking this single spectral characteristic and breaking it into 3 pieces, depending on the geometry of the orbit. A lot of what we can observe boils down to beating between these different frequencies. So if you know a little bit about studies of gravity in our solar system, one of the most important things that Einstein helped to understand is the perihelion precession of Mercury. Well, that perihelion precession is completely described by the difference between the phi frequency and the r frequency. So here's a little movie of a body moving on an orbit where you can see this in effect. Okay, so this is actually something which is a little bit inclined, it's eccentric, and you can see the way that different frequencies don't agree with one another, so the orbits don't close, they form these kind of rosettes. So what we need to do is figure out a way to efficiently calculate all these orbits and then calculate the gravitational waves that arise from them and how the gravitational waves back react on the system. So this is where I now put in the first order corrections to these things. And what this does is it puts in some forcing terms that pushes the motion away from these perfect geodesic orbits. And I get some other forcing terms that cause my conserved quantities to dissipate. Okay? So, like for instance, when my C here is equal to energy, this gives me at leading order the quadrupole formula for gravitational waves carrying energy away from a system. Okay? So, but I'm doing it in a much more formal way that puts everything together. So these we can then go in and we can sort of organize these things by time scale, help us figure out which drive long-term evolution of the system, which are sort of shorter oscillations that happen on a smaller time scale, and help me to organize this calculation. And so what we find, one of the most important things, pardon me a second, one of the most important things that arises out of this is an understanding of how the gravitational wave phase accumulates over an n-spiral. So let's say I just want to know sort of the leading phase term, an integral of a particular common, yes?
Just this previous slide, yeah. Just to clarify, these terms, of course, are going to be derived very explicitly. Right?
Yes.
You're writing them in this very general form, but ultimately these are a set of coupled equations?
That's right. That's absolutely right, yes. I'm not going to go through the details of what they are, but I'm going to show sort of the way in which we can derive them and then use them.
Okay. And there are no additional, because of the fact that you start off with an axisymmetric system, but then you're including all of these other perturbations, right? So you're not using any kind of symmetry in the perturbation at all, right? So or are there hidden symmetries?
There are some hidden symmetries in there, yes. And those are that helps us simplify things, and it's one of the things that makes the calculation. So in particular, one of the things you find is that this term ends up being the leading most important thing. The symmetries, which I'm not going to call out exactly, but because the background space-time is axisymmetric and time stationary, that really simplifies many things that go into this, and helps. The equations that govern this actually start out as partial differential equations, but I can then separate them and turn them into a set of ordinary differential equations. And as a colleague of mine likes to say, a colleague who does numerical analysis, if you have an ordinary differential equation, that's an analytic solution. Okay, that's a little bit overstated, but he does make a valid point that many ODEs, as long as you understand how to apply boundary conditions and solve them properly, you can calculate them off into machine precision. And that's one of the things we take advantage of to do this. Okay, so what I want to do now is take this whole thing and show the way that these different effects sort of integrate up and accumulate. There's a leading order term, which is basically what I would get if I just took the kind of orbits that are described in textbooks, and I allow the leading dissipative back reaction to act upon them. So when we do this, we get a sort of contribution to the phase whose numerical value scales as the inverse mass ratio. So in other words, the larger, the more extreme the mass ratio, the greater the phase that you would accumulate in your measurement. So if you have a system with a mass ratio of 1 to 10,000, it would accumulate 10,000 times as many cycles as well as with a mass ratio of 1 to 1. We call this adiabatic because this essentially can be thought of as just the kind of orbits you learn about in a general relativity class that are slowly evolving. We then find that there are two terms that contribute at the next order. One of them involves there's another piece of the first order correction that I didn't talk about too much. It's a little bit more challenging to calculate, but it's something we know how to do. And then it turns out there's a second order piece that enters that affects things at exactly this order. I'm going to come back to talk about this briefly a little later in the talk, but the fact that I'm already sort of worrying about second order should be a hallmark, should be a signpost rather, that here's something where it's going to get challenging. So we call these the first post-adiabatic effects, okay? I'm going to focus on, well, let me just say where the things stand today. So the dissipative thing, the adiabatic order stuff, 100% understood. We actually are in the process right now of developing, in concert with those who are working on the LISA mission, a family of waveforms based entirely on this adiabatic approximation in order to begin mapping out the measurement problem to develop some of our analysis software. It won't be enough. We actually know that we need these things as well. But these, as I'm going to describe in the next 15 or so minutes, we can calculate quickly, and we understand how to do them. We can use this to sort of at least study our parameter space. The first post-adiabatic term, we understand how to calculate this. It's just hard. Okay, and when I say hard, it basically comes down to sort of technical problems having to do with understanding how to detailed calculate the self-interaction of a very small, sharp perturbation of space-time with itself. At second order, this is particularly challenging because in order to do second order, some of your source terms are first order coupling to first order. So you need your first order done to very high precision in order to get second order at fairly crude precision. So the first results of this have recently been published, and I'll tell you why I'm optimistic about this moving forward. So I'm going to start talking about results now. So how do we describe these adiabatic waveforms? This kind of comes to some of the questions you were just asking me about. So I can think of the leading order approximation to these things as I just take a black hole orbit, as described in my general relativity textbooks, I allow it to sort of slowly evolve due to this self-force formalism, and I just track through a sequence of these orbits. Okay, you can kind of think of it as saying, suppose I start at some point in this parameter space. So the parameter space I'm showing you here describes equatorial orbits of a rapidly spinning black hole. The horizontal axis describes a separation. The vertical axis describes an eccentricity. I start at some orbit. Gravitational waves tells me that this evolves to some other orbit, and it sort of traces through a whole bunch of points until eventually it hits an instability and plunges into the big black hole. The one technical detail I will go into is that there's work by Tucholsky done in 1973 that shows us how to calculate this self-interaction. And so what it basically boils down to is this is the quantity that I find by solving one of these ordinary differential equations that comes out of the symmetry reduced form. This is sort of like a spherical harmonic, but kind of a spherical harmonic that's doing strange drugs. It's just kind of, works on a different basis, but it's very, very similar. And then, EVIM phi, et cetera, those are all really, really simple. This is actually one of the ways in which the symmetry helps me, the fact that I've just got Fourier bases for my time and the axial direction. So here's an example. What I can do is sort of say, what do the gravitational waves look like at various points in the parameter space? So up here at this dot, if I look at a few cycles of the gravitational waves here, you can see this is a very eccentric source. And so I get this behavior where when it's moving near its periapsis, it's moving very rapidly, and I get this high amplitude rapid wiggle. Then I get a much slower varying, lower amplitude wiggle as it goes back out to periapsis, back out to apoapsis, and then back in again, and I get a very high frequency wiggle. Down here, I have much lower eccentricity, and I end up with, this is the gravitational waveform for, believe it or not, a nearly circular orbit. Now, why is it that the amplitude is so much higher on half the cycles than on the others? Well, this is whirling very deep in the strong field of a rapidly rotating black hole. And so the body, as seen by distant observers, is actually moving an appreciable fraction of the speed of light. And what you're seeing here is essentially a synchrotron beaming effect. The gravitational wave pattern is actually beamed into a narrow angle. And so as it goes around, at certain points, you get the wave pattern really slamming into you, and that's where it happens at high amplitude. And then it's a little bit lower, and then that beamed pattern crosses over you again. Okay? Even if you were at 0 eccentricity, you would see this exact same pattern. One of the things that this highlights, though, is that in order to calculate this precisely, you need to compute a lot of harmonics. Okay? That's why I have close to 13 million gravitational wave harmonics computed over this set of just over 1,400 orbits. So once I have this put together, all I need to do is set the initial conditions for where my orbit starts, say, Einstein, go to work. And the system will then evolve down like this. Ta-da, I've generated, yes?
Are we still talking about extreme mass ratio?
We are still talking about, for the rest of this talk, we are always talking about extreme mass ratios, unless I tell you otherwise, which I will at some point. Good question. Yeah?
This use of the curve, of
Yeah.
the orbits, the fact that this is adiabatic is also reminiscent of the early PPN calculations.
Isn't it?
Where
Yes.
we had exactly there, of course, it's in the Newtonian limit that
That's
you
right.
get different orbits as you come closer, and then
The,
here.
the conceptual foundations are very, very similar.
Okay.
Absolutely, absolutely. Yes. That's one of the reasons why the extreme mass ratio is a fun playground to work in, because you have this not quite exact, but really good, you can kind of think of the black hole geodesic orbits as a set of basis functions that you're working with. And that's essentially what we're doing. So when I follow that thing, this is the gravitational waveform that I actually get. And the key message I want to point out is that we can do this for a tremendous number of orbits now. We put the whole thing together, and you can even make a little movie of what the system looks like and pair it up to the gravitational waves. Now, one of the things, I just want to give you a little bit of a warning, one of the things which I like to do is gravitational waves. If you look at the LIGO signals, they're in a frequency band from 10 hertz to 1,000 hertz, which is exactly the sensitivity of the human ear. So a really useful way to understand the spectral content of these waves is to turn them into a sound. This would be a LISA source, and so it would be at sort of the millihertz or centihertz band, and the system would last a year. I need to go home before that. So what I've done is I've boosted up the frequencies to put them into the human audio band. So what we're going to do is watch a sped up version of one of these inspirals and the gravitational waves it produces. The buzzing that you hear as this proceeds is largely because it has much higher amplitude as the small body moves near periapsis than when it goes out to apoapsis. It's also because we're doing this for a rapidly rotating black hole. There is a modulation imposed by the rotation of the orbital plane up to a flame drive. A big black hole whirls the orbits around. Now, as time proceeds, the eccentricity gets smaller, and so some of that buzzing is a little less dense. High amplitude periapsis is not significant for low amplitude apoapsis. And then it plunges into the big black hole. So what we want to do is generate millions of waveforms like that. Yes.
In the PPN
think you-
sorry, in the PPN case, there you kind of had to stop, and the merger part was not you can't use the analytic calculation. But here you're using it all the way to the end.
So what I'm actually doing in the calculation that I just showed you, I do actually stop it just as it begins the merger. We are working on, we understand how to go a bit beyond that. We do need to sort of switch to a different horse in some sense in order to do that, because some of our assumptions about, essentially part of what goes into this is an assumption of a separation of timescales between the orbit and the back reaction. When it begins to plunge, that separation of timescales no longer exists. I think I don't have slides that I'm planning to present here, but I have some of my backup slides. And so if you want to talk about this more afterwards, I'd be happy to do this.
So, related question was,
Sorry.
why does the simulation not just go haywire when the approximation breaks down? It still plunges into the black hole, right? So there must be some
Well, what it actually does is it stops. The approximation that we're using to generate that, it starts to become invalid as you approach the last stable orbit. Okay, so in Schwarzschild, that's famously at 3 times the Schwarzschild radius of the horizon. For Kerr, it's a bit of a more complicated function. And so what we do is we sort of stop it there, but we know that we know how to calculate at least a good approximation for how it sort of transitions from that into a plunging trajectory that goes into the black hole. So that's what we do. We just attach it. And in this particular plot, it's a relatively crude thing. We're working on refining that now, but it's good enough for visual purposes, and that's what we do. So one of the things that I want to emphasize about this, and this ties into what I think is sort of important as we think about gravitational wave modeling, not just in the extreme mass ratio, but more broadly, is that the waveforms are very, very complicated, but they involve a very simple structure that is essentially, it's just a superposition. So this big mess of many, many oscillations that evolve in this way can be thought of as a superposition of many voices. And each of these voices, that's one of the reasons I like to do things audially, every individual voice in this chorus evolves in a very simple way. And so if I look at a couple of the most important contributions to that waveform, they have amplitudes that grow in a very simple way. They have phases that grow in a very simple way. And that tells us that when we generate all these data, from a computational standpoint, they can be sampled much more sparsely than you would sample the total waveform itself. This enables us to develop techniques for computing these waveforms that are extremely efficient. Now, I have to do a pre-computation of the data that describes the back reaction and the waveform amplitudes in advance. That might take hundreds of thousands of CPU hours. But then I store it. So if I go ahead and I do this, so we make this gravitational waveform, I did this by sort of the most dumb way possible, where I just computed every moment at every moment in time, not taking advantage of the smoothness of these things. And I did it on my laptop. Okay, and making that waveform that I showed you took about 3 hours when I did that. By taking advantage of the smoothness of these things, developing some high-order interpolations, using GPU programming in order to sort of really speed things up, we can make a waveform that is 100% in phase with this thing over 25,000 orbits in approximately 50 milliseconds. So this underlays a program known as the fast Emery waveforms. Now, you had asked a few moments ago about whether this is for extreme mass ratio or for the general mass ratio. This is definitely for the extreme mass ratio. But I think a lot of these techniques, they're very similar to the things that people are using today to understand how to do very smart constructions of surrogates that describe the kind of waveforms that LIGO and Virgo are measuring today. So it all kind of comes down to understanding the behavior for waveforms and finding a smart way to describe your data so that you can build your calculator. So let me tell you a little bit about some of the physics that goes into this. So when I actually computed that sequence, what I did was, I computed sort of the orbit average self-interaction of the small body back against its orbit. This can be thought of as being due to radiation that goes off to infinity and radiation that is absorbed by the black hole's event horizon. I want to talk about those two contributions for a second. When I look at the radiation to infinity, it always takes energy away from the body. Kind of makes sense. Just think about electromagnetic intuition. If you're radiating dipole, the dipole carries energy away from the system. When I look at the flux going into the horizon, the sign is not definite. If the orbit is in some sense faster than the event horizon, remember this horizon is rotating, so as seen by distant observers, you can ascribe a rotation frequency to it. If the orbit is faster than that hole, then it's just like the radiation to infinity. It takes energy out of the orbit. But if the orbit is slower than the hole, it actually puts energy into the orbit. This is actually, in fact, not a small effect. One thing we found when we first began looking at this is that if I just sort of imagine, I go into, I find a secret closet somewhere that says, event horizon coupling. And I go in and I turn this horizon flux, I sort of get a hold of God's knob or something like that, and I change it from 1 to 0. What we find is that in a case where we get energy from that event horizon, it changes the duration of the in-spiral by weeks. It changes the number of cycles that are in band by tens of thousands. This is a non-negligible effect. And indeed, I've been working with currently a postdoc in Italy, Shayak Dutta, to do a detailed analysis of whether we can measure this precisely. And what we can find is, imagine I sort of put a parameter in front of this and ask myself, suppose I want to test the boundary condition on the event horizon. What Shayak and some of our other collaborators and I have shown is that we can probe that boundary condition at like part in 10,000 level precision. So this is fascinating, but it sort of makes you wonder, what is really going on here? One thing which is beautiful is that you can actually recast that radiation that goes into the horizon as a tidal field of the secondary acting onto a black hole. So let's think about tidal fields acting on a fluid body. So if I have some flowing fluid, imagine I just have a fluid planet or something like that, a planet made entirely out of water. It's rotating and it has a moon orbiting around it. That moon will exert a shear, will distort the flow lines of the elements of that fluid. And if the fluid has any shear viscosity associated with it, that shear viscosity will couple to the shearing of the fluid elements and it'll generate heat. This is tidal heating. Okay, it's through this mechanism that the moon is gradually slowing down the Earth's spin. That's why the moon is actually receding away from the Earth very, very slowly. So black holes are not fluid bodies, but we can think of them as being described by a two-dimensional fluid of light rays that generate their event horizons. And so the behavior of these things is governed by the Raychaudhuri equation. And so when I write this thing out in its general form, this tells me about how the expansion of a bundle of light rays behaves as it moves through space-time. Hawking and Hartle showed that when you apply this to a black hole, you can change this into a function that describes how, so remember, there's an expansion associated with this. If there's a shear that is applied to those generators of the event horizon, it will change the area of the event horizon. There's a coupling constant that emerges from this, which is known as the surface gravity of the black hole. Now, Bekenstein and Hawking conjectured that that surface gravity can be related to a temperature for the black hole. And the area can be related to an entropy for that black hole. So if I put all these things together, what I find is an equation that looks identical to how heat and entropy are generated in my fluid body, but now it is not a fluid, it is the sort of pseudo-fluid, a two-dimensional pseudo-fluid that is actually the event horizon of the black hole. And there's a viscosity parameter that enters. This actually has the dimensions of viscosity for a two-dimensional fluid, which is nothing but the speed of light and Newton's gravitational constant. So you can kind of think of what's going on here is that the event horizon is acting as a very viscous two-dimensional fluid. And I can take advantage of this to actually ask myself, when I calculate that flux down the horizon, does this tell me about a tidal coupling of the black hole and an orbiting body? So a former student of mine spent some time thinking about how to use these things. So here we're going to see a little body coming in near a black hole. And indeed, what we find is that this allows us to calculate how this shape distorts. And the geometry of that distortion then back reacts on an orbit in exactly the way that it needs to do to account for the kind of weird effects that we see with the flux of energy going into the event horizon or coming out of the event horizon. So there's a beautiful little bit of physics that is really encoded in the strong field nature of event horizons. Well, in my last couple of minutes, I want to talk a little bit about what we do going beyond this adiabatic model. We know this is not enough for us. Indeed, when we look at the post-adiabatic bits, about half of it comes from first-order perturbation theory, but another half comes from second-order perturbation theory. Second order is always very difficult because to get second order right, you have to have first order really, really precise. This can finally now be done for simple cases. Okay, so a couple years ago, some of my colleagues published the results where they developed the first post-adiabatic terms and computed the gravitational waves for circular orbits in the Schwarzschild spacetime. So what I'm showing you here, the red line is results calculated using this perturbative expansion, first order plus second order. The black line shows what you get when you calculate the evolution of two black holes using numerical relativity. Up until near the very end here, where there is a little bit of a breakdown, this is related to that breakdown in timescale I was alluding to earlier, they are perfectly in sync with one another. And just to sort of show that it's a non-trivial effect, the blue curve shown here is what happens if you only do first order. Now, one thing which is hidden in this figure is that this even works when the mass ratio is not small. I've been doing all this, I've been telling you this is black hole perturbation theory. And indeed, for these sources, I've largely been thinking of mass ratios of like 10,000 to 1. This calculation is a mass ratio of 10 to 1. And they've actually shown it works pretty well when the mass ratio is 3 to 1. This seems to be suggesting, at least empirically, that the next post-adiabatic terms are probably much less important, and that this seems to gather up much of what's there, at least for this configuration. I think it's worth emphasizing that this is about as simple as it gets. Last thing which I want to quickly just go through is that the systems I've been talking about are almost a Platonic ideal of a binary system. I have a black hole, and I have a point mass. Astrophysical bodies are not point masses, okay? And so we need to include some structure that goes beyond that. And so among other things, you need to start thinking about the fact that these bodies have a finite size. And so there is efforts in this regime. So the leading structure that goes beyond just being a point mass is, imagine it's a body that's endowed with some spin angular momentum. So when that's the case, the zeroth order equation of motion, just what you get from the GR textbooks, it's not just the geodesic, but you get a forcing term that involves a coupling of the angular momentum of the body to the space-time curvature that it moves through. And you find that that angular momentum precesses. So this ends up giving us additional forcing terms which change all of our orbital frequencies, and they actually give us an effect that's comparable to the leading self-force. This is actually something we've understood for quite a while from the post-Newtonian regime. Okay, so this ends up having a mathematical structure that looks just like magnetism. So I can think of a body's angular momentum as being kind of like a magnetic dipole moment. As it sits in a space-time, that magnetic dipole moment-like structure couples to space-time curvature, and it precesses. Now, you may recall from undergraduate electricity and magnetism that if you have a magnetic dipole moment in a magnetic field, it feels a torque, mu cross B. Well, I'm talking about angular momenta, and so the torque is the rate of change of the angular momentum. Well, I basically have a torque, one term arises from the orbital motion of the body, and another torque that arises from the other body's spin. So this leads to new forces and modifies the orbital acceleration that it feels. But it conserves global angular momentum, at least on time scales where it can sort of neglect the back reaction for a few moments. And so what we find is that S1 and S2 wiggle around in my binary. The orbital plane has to wiggle in such a way that the sum remains fixed. So there's a little animation illustrating this. So what I'm going to show you here, over here on the left, these blue streaks are going to track the motion of two black holes that are orbiting each other. The magenta stick is the normal to the orbital plane. So that's the orbital angular momentum vector. Over here on the right, I look at the spins of the two individual black holes. Those are the orange sticks. And this, again, is that normal to the orbital plane. This green is their sum, at least the direction of their sum. So what we see as we integrate these equations forward, the spins precess, the orbit precesses, and it does so in such a way that their sum remains perfectly fixed. So as these things are spinning around, because the orbital plane is wobbling like this, this modulates the waveform. It causes the ratio of the polarizations to vary over time. I'm going to go through this fairly quickly. We can do this as well when we have a small spinning body, and so I'm going to skip through this fairly quickly. The lesson I want to make is We know how to calculate this, and we're now folding this into our framework as well. We're at the point where we can actually calculate very long gravitational waves, at least using sort of an approximate in-spiral. We're now working on improving this. So these things don't exist in a vacuum. And I just want to conclude by showing some really cool recent results my X-ray colleagues have discovered. So over the past several years, we have uncovered a variety of systems which exhibit these really regular flares. So this is a particular source. There was a tidal disruption event occurred in 2019. And it flashed in X-rays every 9 hours after that. Something that is that regular of a clock, it's kind of hard to think, what might be that regular? And so a very plausible hypothesis is that you have some kind of an orbiting compact body that every 9 hours or so is interacting with material that was left behind after that star disrupted. There's other sources where they're not quite as regular than that. But a graduate student who I do a little work with at MIT, Johin Chakraborty, has shown that you get a really wonderful fit if you imagine that in that case, the accretion disk is a little bit tilted, and there's a precession of the disk, and you have a precessing orbit interacting with a precessing disk. What's particularly exciting about all of these is that these are essentially the progenitor of many of these events that we'd expect to see. There's one last one which I'm going to show, which looks like it was a tidal disruption event in March of 2018. It showed this sort of quasi-periodic oscillation that was consistent with an orbit near the last stable orbit of a Kerr black hole. But with time, that frequency evolved. If you're a gravitational wave theorist, you would say it's evolving the wrong way. This is the system that's actually moving to larger radius rather than in-spiraling. However, that's exactly what you would expect if it's an object that's transferring mass from itself onto that big black hole. What's particularly cool about this particular object is that when you look at the frequency that it's at, this would be right in LISA's band. I think this is a really exciting example of the kind of thing where combined electromagnetic multi-messenger observations could really teach us something. Well, I'm at the end of my time, so what I want to do, I didn't even realize I was speaking at the beginning of this sort of thing, but I wanted to really, I think, emphasize that over the past 10 years, observations have allowed us to more effectively and thoroughly probe strong gravity than ever before. There's going to be future measurements that allow us to go deeper. They're going to involve a lot more detailed physics than we have put together. And so we really need to develop a framework for measuring these things, keep our mind open so that we are not fooled by things that look like new physics but aren't. And here I have to confess, I have an advantage over many people, because I have a family member who, it turns out, has an innate ability to model these things. And so for those of you who are supervising people, get your students started when they are young. Thank you.
Thanks, Scott. Do we have any more questions? Use the microphone, yeah?
Yeah.
You spoke about the mass and the angular momentum of the black hole, but there's also charge. So is there any merit to considering non-neutral black holes, and if they'll influence the signal in a different way?
So the assumption that is used by essentially every astrophysicist is that because so many environments that black holes live in are, they're imbued in an interstellar medium that is rich with charged particles, there's a lot of plasma that's around, any non-zero charge will tend to be neutralized by the interstellar medium, the intergalactic medium on some kind of a time scale. Now, you can then turn that around and say, well, can we test that? And I would say that there's a priority list of things that need attention quickly, things that are interesting that maybe you do a little bit later in your career. For me personally, I put that sort of a little bit lower down because one thing that we found is that every one of the kind of events that we've measured is completely consistent with a neutral black hole. We do know, for example, that like the final ringing spectrum of a black hole, it changes somewhat if it's charged. And we don't need to introduce that to get good fits to the data. So that seems at least consistent with this hypothesis that if there were a charge, it would be neutralized on a time scale consistent with human observations.
Hi. Are there mass ratios for which the inspiring signal is very different? Like looking at the, let's say, cutoff frequency before the last tail?
Yeah, so the cutoff frequency depends on the total mass of the system. So what the mass ratio determines is the rate at which you sweep through your band.
Okay.
So if you tell me the total mass of the system, I'll make a prediction for what the frequency is. That ends up being then independent of the mass ratio. Maybe there's small corrections, but it's essentially independent of the mass ratio. But then the rate at which I sweep through this is totally determined by that mass ratio. That's one of the reasons why these sort of very small mass ratio models we look at, they're expected to be in band for tens to 50,000 orbits kind of a thing. The LIGO type sources that we're measuring, the ones that have a mass ratio of 10 to 1, they might have 25 cycles. The ones that are 1 to 1 might have 6 cycles.
Thank you.
I will comment, that's one reason I think many people are very eager to push the low frequency sensitivity down, because if you can have it come into the band earlier, you gain a lot of signal. Yeah.
When you have extreme mass differences in two black holes, in different situations, for example, when the small black hole is inside the ergosphere compared to when it's outside, is there any change in the signals as you're working the frequency?
That's a great question. When I initially started studying those, I dreamed that I would find some kind of a signature that made it clear whether you were inside an ergosphere or you were not. And the answer to my young postdoc self, disappointingly, was no. And I think I understand this finally now. And one of the main reasons for this is we are measuring these things. What we are not really measuring that point. What we're measuring is a gravitational perturbation that's got a length scale that is set by that point, but is quite broad and dispersed. And then we're measuring gravitational waves that happen on a length scale that's determined by the properties of that orbit. So even when the small body is inside the ergosphere, even when it's outside the ergosphere, it's generating a gravitational perturbation that is both inside and outside. And so you sort of pick up a little bit from inside, a little bit from outside. And so my dream was that there would be some really sharp marker and sort of go, aha, that hit the ergosphere. And no, it just doesn't work out. I mean, things evolve in a much smoother adiabatic fashion. And I think it's just because of the fact that this perturbation sort of, if I may use the term, it sort of tastes both space-time inside the ergosphere and outside of it.
Thank you.
But I shared your dream.
Isn't this negative energy flux into the horizon related to the existence?
Yeah, so what that's related to is the existence of superradiant modes, which can only exist if there is an ergosphere. Yes, yes. And it's kind of a balance, which ones are the most important. Yeah. But when you're just getting to that question, they sort of exist even for orbits that are outside the ergosphere. Yeah.
Just the flux going in.
Yeah, yeah. Sorry, go ahead.
Yeah. I had a very simple question. So whenever we have a single black hole in an asymptotically flat space-time, I define its mass essentially by the ADM mass of the space-time. Now here we don't have anything close to that. We have two black holes which are in a very dynamical space-time. So how do I even define a mass or a mass ratio?
Hang on just a second. I want to go back to a slide I put up really early on, because you, sir, just asked one of the most probing questions that's related to this. It's, hang on just a second. Here it is. So this paper I highlight here by Thorne and Hartle, it addresses exactly the point that even defining mass and spin when you have two black holes in a binary system is ambiguous. You cannot do it precisely. What you can do when they are widely separated from one another, even though the space-time, what you sort of do is you can take advantage of the fact that the space-time, even though you're not quite in an asymptotically flat region, if they're very widely separated from one another, there's a region where it's nearly asymptotically flat. You can evaluate your Komar integrals, you can get your ADM mass and your spin based on that, and get something that is very close to what it would be if that black hole were completely in isolation. It relies on them being widely separated from one another for that to work, though. And as they get closer and closer together, one of the things that this paper shows is that there's a built-in ambiguity, just even in what it basically boils down to, this really related to the fact that it's not a two-body problem, it's a one space-time problem. What you're trying to say is this space-time has a mass of 63 solar masses confined to here. This one has a mass of 62 solar masses confined to here. You can't actually do that in a unique way. So that actually, best you can do is you can do that up to a certain level of ambiguity, and that ambiguity always is going to color this. It becomes one of the reasons why the extreme mass ratio is a nice limit to work with, is that that ambiguity kind of goes away as the mass ratio gets small. That's one of the things, like I said when I gave this slot, you guys thought I was joking, but I was quite serious. I'm a bit of a lazy person. I like working with something where those ambiguities don't actually influence what I'm trying to do. This is one of the things that makes interpreting data from numerical relativity tricky. Because two simulations might think they're doing the exact same thing, but if they use like different time slicings or something like that, they might define the masses differently.
Thank you.
Oh.
What has changed in the last 10 years in our understanding of massive stars that allows for formation of these massive black holes? And is there a preferred redshift range where these are likely to be produced?
So this is hinted at in the text that is in this conference proceeding that depressed 27-year-old me. Okay, so what they found in these old analyses is that when you have massive stars evolving, there are very strong stellar winds that carries away a lot of mass and that changes the way angular momentum evolves in the system, such that if you do have a pair of massive stars that evolves into a binary black hole, that black hole would be so widely separated, it would have so much angular momentum, essentially, that it would not merge in a Hubble time. That was the standard lore as of 1998 or so. What changed was an appreciation for what the opacities were in the atmospheres of massive stars, which changed the way that stellar winds impacted their mass losses and impacted their evolution. I'm not an expert into some of this stuff, but I've at least read the abstracts and the introductions of their papers well enough to understand at a superficial level that starting around 2008, continuing to about 2012, people had a much better understanding. Part of it has to do with an understanding of what the metallicity distribution was likely to be for the stars that would produce these kinds of black holes. I think these were sort of assumed to have like solar-type metallicities. In fact, they were probably they were probably from an earlier epoch, and they probably had much lower metallicities. And so you change those opacities of the stellar atmospheres, not as much mass is lost, and better modeling of the angular momentum transfer during the evolution of the system led to them not being as widely separated when they formed black holes.
So from the population of massive black holes that have been detected with the gravitational wave, is there likelihood that at least a few of these will be detected in the nearby observable universe electromagnetically?
I think most of them are still, they're still hundreds of millions of parsecs away. And so, they are still on a per galaxy basis really rare. And so I think that's an excellent question. I've never seen anyone address it. And so when I say that, that's just remarking why I think that you might still be able to sort of evade some of the limits that might be interesting to be put on that. Yeah, I think that's right. I think it's still probably, if you look at the phase space of stars, it's still a really small sliver of the parameter space that's likely to lead to binary stars that produce binary black holes. Just so happens if you have a gravitational wave antenna, those binary black holes are really loud. So, we kind of have a selection effect where we're able to detect them. But I think that because most of these are in quite distant galaxies, having, telescopic observation of them they're also probably very short-lived stars, right? Because these are going to be massive stars. So they probably only live a few tens of millions of years. So you have to probably be lucky to get it.
Question back there.
Yeah, hello.
Hi.
Yeah, so I want to ask you some doubt. So this LIGO detections, when it happens. I have seen some detection happened in more than 2 observatory. Like, so can we do the localization at least towards one direction or something?
So yeah, so you're asking essentially how well can we localize?
Yeah.
So the more detectors you have, the better you can localize.
Yes.
Okay, that's the first thing. And indeed, the 2 LIGO detectors on their own are terrible for localization. Now, there was a design choice that was made when LIGO was first constructed. So they basically put there's 2 detectors, one in the western part of the United States, one in the southern part. They're at different points on the globe, so what I'm about to say is not 100% true, but they were essentially designed so that their arms would be parallel to one another in order that both would measure the same linear combination of gravitational wave polarizations. If your goal is to detect an event, that's a smart choice, because what it does is that it maximizes the signal-noise ratio in that polarization. If your goal is to get information about the 2 polarization, that is the worst possible choice you could make. I often wished that the site in in Washington State's in a big desert. It would be lovely if they could build it on a turntable so they could just rotate the whole thing. If you could rotate it by 45 degrees, it would be almost perfect. So right now, the 2 detectors in the United States effectively act like one. There's a little bit of information, actually not a little, you actually get a significant amount of information because there's timing information. So a wavefront that crosses the Earth, it will hit one detector before the other. And from the timing information, that tells you a sort of a sphere, at least that gives you a great circle, rather, on the sky that allows you to, of where it would be located. The Virgo detector, which is at somewhat lower sensitivity, in combination with those 2, make sort of complementary great circles. But they're relatively fat, and so the localization at the moment tends to be in multiple degrees, which if you're an astronomer, isn't good. If you add a site in India to this, it massively improves the ability to do that, simply by timing, because it's so widely separated from the others.
One more, my interest is if we able to tell the direction. We are sampling pulsars, millisecond pulsars for last 15 years.
Right.
With a precision of few nanoseconds. So is it possible to search for any correlation towards the direction of these events? That is what.
I'm not sure. It's a good question. Yeah, I'm not quite sure. I mean, the localization from gravitational waves, at the moment, the system that was localized most accurately was the binary neutron star event. And that was in part due to luck. So when that event was actually measured, the Virgo detector in Italy, it measured an event with signal-noise ratio of 0. Now, that could have meant that it was broken, but it actually meant that the system was located, the sky position of the actual event was in a null of the antenna pattern. And that was a case, this did not go over well when they tried to argue with their funding agencies, but it was one of those cases where the absence of a detection was actually very powerfully informative. And it helped people to sort of narrow down where it was to an array of about a dozen galaxies. And indeed, when they looked at them, they saw an optical afterglow next to one of those galaxies. So asking about correlating it with something that we know in the sky as precisely as a millisecond pulsar, I think we're probably not quite there yet.
Oh, thanks.
So I'll just ask the question that I've been meaning to ask, which is actually more a comment on your last statement and also the first statements that you were making about GR and the veracity of GR.
Yeah.
Which is very, right now we see a lot of sort of work that people seem to be doing in calculating things that are beyond GR in such systems. And one of the questions one always wants to ask, and it's really nice to have heard the talk and the kind of messier systems that are actually being calculated, is how much of this could be attributed to just good old-fashioned GR plus other things that you've not looked at, because the simplest class of waveforms are, of course, simplified, and there's so much more astrophysics and so on going in here. And so I think you've kind of answered that, but I just want to know, there's still there's still an effort to bring out waveforms and so on in these modified theories, which seems to be at some level, I mean, there's two questions there. One is whether it could be easily explained, or more not easily, but at least explained through standard physics, GR, but also whether the scales at which one is talking about these effects. I never understand why you expect new physics at the scales of astrophysically relevant black holes. I just want to know what your opinion on this was.
I'm trying to decide how polite I want to be in my answer. You're always, of course, reminded of the parable of the drunk who lost his keys, and he's looking at underneath every light post, and the police officer says, "Why are you looking here, sir?" He says, "Well, this is where the light is good." I kind of feel like a big reason why people are looking there is this is where they are getting data that they can approach in there. And so, to be blunt, I think some of these models they're not driven necessarily by the physics that we would expect to modify GR. They're driven by the fact that here's where I'm getting data that I can hope to set a limit. And, it's maybe you're going to get lucky and there'll be a convergence of those two things. But, I mentioned the bet that I would do with the money I have in my pocket right now. So I feel like you and I are on the same wavelength about this. Yeah.
Yeah, just to follow up on his questions, something which clicked. So you said the LIGO polarization, the two antennas in the US have look at the same polarization.
Right.
So the one in LIGO India will be looking at a different one?
I believe so.
Okay, and on the follow-up that,
if nothing else, pardon me, I'll just interrupt you. I mean, because it's such the two detectors in the United States, there's not that much curvature between the two of them as well. So it's a little easier for them to be parallel. It's almost impossible to make it have the same polarization just because it's on such a different part of the sphere. So, I don't know what the geometry is likely to be for this thing, but I hope it's being designed to kind of maximize an ability to pick up a difference of polarization. That would be most valuable in my opinion.
Yeah, and then following on that, so if you end up detecting two polarizations, like the two different polarizations, does it, particularly in terms of BNS mergers, where you're looking for electromagnetic counterparts and you're interested in the inclinations because that would tell you whether you will get a GRB or you will just get... So will that information, does the polarization will matter there, and you'll get that in terms of triggers, is it what the inclination of the system is does that get?
So as far as what information is included with triggers and things like that, I would like for that information to be contributed. I am not a decider on this, though, so I think that's that's a scientific policy issue. One thing we have to be a little bit careful about is that when they send out the triggers, they do sort of a multi-tiered inference analysis. And this would probably be a relatively fast, crude analysis. And so what they might do is provide sort of a first estimate of a polarization ratio. And a polarization ratio, so if I have a binary that you see edge on, you only get one polarization. If you are, so if it's kind of like if you're seeing something that's moving like this, you only get one polarization. On the other hand, if you're seeing this face on, you would get two polarizations. And so from the polarization ratio, you would know where it is between those two things. I don't know if they're designing things such the alert would include that information, but you look like you're probably younger than me. If you have any influence on people who are making these decisions, you just made what I think is a really compelling argument for why they should do that.
Thanks.
Hi, thanks for the great talk. So I wanted to ask a question about the environmental effects.
Yes.
So for example, in the QPE systems, as you mentioned, there is observed out spiral.
Right.
This is for example, a well-defined source, and we might be able to detect gravitational waves corresponding to this. But when we don't know a priori about the existence of such a source, then we have to do, I suppose, the very well-defined modeling and
yes.
of the...
Well, one nice thing about that particular source is that it appears to be, if it is sort of an orbiter that's causing this kind of behavior, and I think that's a big if. It might not actually be that. That's an interesting hypothesis, but it's one that we can test relatively easily. A lot of the modeling that I described becomes really easy if the orbit is simple. And this appears to be a circular orbit that is confined and trapped in an accretion disk. So a lot of the complications that lead to these self-force calculations, the modeling I'm doing, forget it, throw it away. You just have essentially a slowly evolving sinusoid. And so if you were able to detect it, and one nice thing about the way Lisa makes the measurements, it's a long waveform being measured by a detector that is orbiting the Earth. There's a modulation that basically you can sort of demodulate the data to pick out a particular position on the sky. We know where the source is located. And so this would be a relatively easy one to do that kind of hypothesis testing on.
Yeah, but
Now, if there are unknown ones, that is certainly challenging.
yeah, so then like we have to do the detailed modeling, increasing the parameter space and
Absolutely.
Okay. So is there any part of parameter space where do you think like detection can be done, like in 2 steps? Let's say even without that detailed modeling.
That's a great question. Yes.
But in the inference part, we can infer the environment.
So imagine I'm looking at, so there's a couple different forms of environmental effects that I personally have studied. One of them has to do with a body that's interacting with an accretion disk. And in that case, the leading effect that appears to really influence things is that as the body is interacting with the accretion disk, it's actually not even like viscous interaction with the fluid. It's that you set up density waves in the disk, and those density waves exert a torque that modifies the orbit a little bit. If you do not take that modeling into account, the sort of vanilla models that we're making right now will probably still detect it, but with just badly systematic errors in the kind of parameters. That would be perfect for what you're suggesting. We have sort of like a multi-tiered model associated with this. And so what I think you need to do is develop a measurement pipeline that's robust enough to include, you do need to study how these systematic effects come in and have maybe a measurement pipeline that is robust to capture the kind of deformations of the waveform that you would put together for this. Another family of environmental effects that I've thought about, which I think is potentially very interesting, is that when we do these models, our system contains a big black hole, a small black hole, us over here on Earth making the observation, we ignore the rest of the galaxy. In particular, we ignore the star cluster that this black hole is embedded in. There will probably be nearby stars that gravitationally interact with this thing, and they actually lead to tidal perturbations on the system that can have interesting effects, particularly when certain frequencies associated with the orbits go through resonances. Those are ones where I think they have unique sort of impacts on the system that I think would stand out more robustly in the data. And so that's an example of one where I think it would not be as difficult to design a measurement chain that would pull it out.
Thank you.
Sorry, repeat, please.
Just a related question. Won't the environmental effects, wouldn't it show up in the residuals? I come from like atomic physics background.
Yeah.
More often than not, it would show up in the noise spectrum, so to say.
So where it might show up, so this gets to the heart of what I think is one of my main themes, is that we're trying to develop modeling with as few systematics as possible. So suppose I make a model that fits as well as possible and I try to subtract it. If the residual I have left behind still has some kind of signal-like structure to it, the question then becomes, did I do the GR right? Or is there some new physics that I've overlooked? Is there something beyond general relativity, right? And so we kind of have to answer all these questions simultaneously. But you're right. I mean, this is the kind of thing that we would try to look for that might be hidden in that. Yeah.
Are there any other questions? Let's thank Scott.
Thank you.
I think I was supposed to pose for the camera. Should we shake hands or something? I have no idea. It's my first time. You should
Okay, I'll tell you what, we'll hold it together. Thank you. Absolutely beautiful. Excellent, yeah.